Today, we're going to do something a little different. We're going to build an AI supercomputer right here from scratch. Well, a virtual one anyway. We're going to go piece by piece, demystifying the massive, and I mean massive, infrastructure behind the AI revolution, from the humble power plug all the way to the final prediction. All right, let's get into it. But first, hang on. Why do we even need to do this? Why can't we just run the latest and greatest AI on, say, a souped-up gaming PC? And that's really the core question, isn't it? It turns out that the math behind these new AI models is just so demanding, so incredibly huge, that it's forced us to completely reinvent what a computer even is, right from the ground up.
So here's our game plan. First, we'll look at why this explosion in demand for AI happened in the first place. Then, we'll actually blueprint the physical data center. After that, we'll assemble the core hardware, the engine room, and connect its nervous system. Then, we'll install the software that acts as its brain. And finally, we'll see what this incredible machine is actually for.
Okay, so let's start at the beginning. It really feels like this new wave of AI just appeared out of nowhere, right? But the truth is, the seeds for it were planted more than a decade ago. Think of it as a Cambrian explosion for artificial intelligence.
You see, right around 2010, you had this perfect storm. Three things all came together at once. First, GPUs, the graphics cards built for video games, got incredibly powerful and flexible. Second, thanks to the internet, we suddenly had these enormous data sets to train our models on. And third, researchers came up with much smarter algorithms, like the transformer architecture, that could actually make sense of all that data. It was the convergence of these three things that really kicked off the modern deep learning era.
Now, before we even dream about plugging in a single chip, we have to talk about the building itself. You really can't just stick these things in an office closet and plug them into the wall. Planning the physical foundation, the blueprint, is the first and honestly one of the most important steps. And it all comes down to what we call the big three constraints. You've got space, power, and cooling. You need the physical space for literally racks upon racks of servers. Then you need a shocking amount of power. We're talking megawatts here, enough to power a small town. And all that electricity creates a ton of heat, which brings us to the third constraint, a cooling system that can stop the whole thing from, well, melting.
So, how exactly do you cool this beast? Well, the traditional way is just air cooling, using giant, powerful fans to blow air across everything. But for the most powerful, densely packed systems, that's just not going to cut it. The industry is really shifting toward liquid cooling. This is where you pump a liquid through tiny tubes directly to the chips themselves, where it absorbs heat and carries it away. It's kind of like giving every single processor its own personal radiator.
Now, the really cool part is you don't have to figure all this out on your own. You're not just guessing. Companies provide something called a reference architecture. The best way to think about it is like a recipe from a professional chef. It's a pre-tested, proven blueprint. For example, NVIDIA has something called a base pod, which is basically a recipe that says use these servers with these switches and these cables and it will just work. Okay, our foundation is planned, the blueprint is ready. Now we get to the fun part. Let's install the engine. We're talking about the specialized hardware that does the actual, thinking. And this is the fundamental puzzle we have to solve. A really big AI model is way too large to fit on a single chip. So you need hundreds, sometimes thousands of them. The question is, how do you get all of those individual processors to work together so perfectly that they act like one single massive brain? Well, first, you need the right tool for the job. Your CPU, the central processing unit, is kind of like a general manager. It's got a few really smart, powerful cores that are great for handling complex instructions one after another. But for AI, the real workhorse is the GPU, the graphics processing unit. Think of a GPU as a huge specialist team, thousands of simpler cores all working on the same problem at the same time. They're just perfect for the kind of repetitive math that's at the heart of deep learning. So you've got this army of thousands of GPUs. How do you get them to talk to each other fast enough? A normal connection would be a massive bottleneck. That's where something called NVLink comes in. It's a dedicated, ultra-fast data highway built just for GPUs. And to manage all that traffic, you have an NVS switch, which is like a massive highway interchange that lets every single GPU talk to every other GPU at full speed. This is the magic that makes them all feel like one unified system.
And there's one more piece of the puzzle here, the DPU, or data processing unit. So if the CPU is the general manager and the GPU is the specialist team, the DPU is the logistics manager. Its only job is to handle all the boring but essential tasks of moving data around, managing network traffic, and dealing with security. By offloading all that work, it frees up the CPU to focus on what it's good at, actually running the main application.
All right, so we've got our super powerful compute servers all built, but one server isn't going to cut it. We need hundreds of them, all connected together, and that means we need a nervous system that's just as fast and powerful as the brains themselves.
See, the old way of doing networking, using a protocol called TCP, it just can't keep up. It's reliable, sure, but it's really chatty. The CPU has to get involved with every single little packet of data, which adds a ton of delay, or latency. The secret sauce for modern AI networks is a technology called RDMA, Remote Direct Memory Access. It's amazing. It lets one server write data directly into another server's memory, completely bypassing the CPU. This just slashes the latency and makes communication almost instantaneous.
And the two big technologies that make this RDMA magic happen are InfiniBand and ROS. InfiniBand is kind of the gold standard. It was purpose-built from day one for supercomputers to have the lowest latency possible. ROS is a super clever alternative that lets you get that same kind of performance, but it runs over the standard Ethernet cables that most data centers already have.
Okay, let's take a step back. We have the building, the power, the cooling. The hardware is all racked up and wired together. But right now, it's just a very, very expensive pile of silicon and metal. To bring it to life, we need software. We need a command center to make it all work together. And the single most important piece of that software is the scheduler. Just imagine, you have 1,000 servers, and you have dozens of data scientists all trying to run their experiments at the same time. It would be chaos. The scheduler is the air traffic controller for the whole system. It looks at all the incoming job requests and intelligently assigns them to servers that are free, making sure the entire cluster is being used as efficiently as possible.
So, what does this look like in practice? Well, there are a few key tools. There's Slurm, which is a classic scheduler, really popular in the scientific and research worlds. But the modern standard is really Kubernetes, which is fantastic for automatically managing and scaling applications. And then, layered on top of that, you have a whole suite of MLOps tools, which are designed specifically to manage the entire machine learning process and make sure those super expensive GPUs are never just sitting around doing nothing.
Okay, I know that was a lot of new terms, so let's just pause for a quick cheat sheet. Building an AI supercomputer isn't about any one magic bullet. It's about how all these specialized parts work together as a team. On the hardware side, you've got NVLink and NVSwitch getting the GPUs talking, with the DPU handling all the logistics. For the network, you've got RDMA acting as that super fast nervous system. And then overseeing the whole operation is the software brain, the scheduler, making sure every part of this machine is working in perfect harmony.
And we've done it. Our supercomputer is built. The lights are blinking, the hardware is humming, the software is running. But what for? What's the whole point? Let's connect all this incredible, complex technology back to the real-world problems it's actually built to solve.
You know, the life of an AI model really has two totally different phases. The first phase is training. This is the brute force, heavy lifting part. It's where the model learns by chewing through massive data sets again and again for days or even weeks on our giant supercomputer. Then there's the second phase, inference. This is when the model is already trained and it's out in the world, making quick predictions based on new data. That part's actually pretty lightweight. Our supercomputer, this whole thing we just built, is designed for that first brutal phase, the training.
And why does that matter? Because that training power is what leads to incredible breakthroughs. We're talking about things like drug discovery, where AI can identify potential new medicines in a fraction of the time it used to take. Or in manufacturing, where it can spot a tiny defect on an assembly line that no human eye could ever see. It's powering the virtual agents you talk to in call centers. And of course, it is the literal brain inside the next generation of autonomous robots.
So there you have it. From the power and cooling systems of a massive data center, all the way to the software that orchestrates this incredible dance of data, we've built the engine. But this is an engine designed not to move cars or planes, but to process information and generate intelligence itself. And the only question left, really, is now that we've built it, what will we ask it to create for us next?